Because the issue that I want to address, obviously, is the burning question of neutrino mass. There, it's the drama of today, right? Because somehow it seems that in the standard model, and you seem to know already some of the story, fails there, right? It didn't do the right job for what we wanted. So of course that brings us to the question, why, the question maybe, how do I know that neutrinos have the mass? And you guys knew that it's from neutrino oscillations, okay? Okay, remember that it's not really measuring the mass.
Difference.
It's just how do you decide that neutrinos have a mass from oscillations? I mean, what did they see when we speak of oscillations? Just briefly, I don't want to focus today on that. I want to come and do it seriously. I want us to, since you already know that neutrinos have a mass, I want us to address from the beginning the crux of the issue. How would you and I construct the mass for neutrinos? So what happens? Why do we speak of oscillations? Why don't I say that Julian oscillates into Jorge ever? He stays Julian ever. Nobody. Does electron oscillate into muon? No, it stays an electron. So why do we speak of neutrino oscillation? Can a particle really oscillate into another particle? Suppose that you have a neutrino with a well-defined mass, put it on a scale, measure it, will it oscillate into another guy? No. So what happens?
The mass and the flavor eigenstates are the same.
Right, the thing that you produce, well, the flavor is just the thing that you produce.
Yes.
Typically is not a particle, but a coherent combination of such states. Okay, you know, okay, obviously, Alexei told you. And why does that happen? For example, in the sun, why is it that I produce a non-physical mixture of the states and not?
Because we need a precise mass.
Okay, but you produce a particle, you produce an electron in a decay, and not a combination of electron and muon, right? You measure its mass. What is it? Okay, just to remind you, I can speak of two massive neutrinos. Remember, there are only two generations. When I want to understand the phenomenon of mixing and masses, I forget 3 generations, it gets messy. Okay? So, I will have two states of different masses. But what is it that the W would interact with, the weak Lagrangian?
Superposition.
Let's try the analog of the quarks. So how was it in the case of quarks? There will be UC bar, gamma mu, L, and then it's not the S, it's some rotation here, right, that I call Cabibbo rotation. I can call it O Cabibbo. It's called VCKM when there are 3 generations. In the case of Cabibbo, just one mixing angle, and then I will have DS L. And remember we said a number of times that I could something is mixing there. I mean, how did I get to C? Because of the mixing, right? Some things are mixing. Up quarks get mixed among the cells for down quarks. I can never know. The only thing that I know is the relative mixing between the two of them. So I could say that these guys are diagonal and these guys mix. Or I could say this is diagonal, these guys. It's a question of language. Okay, there is no way of knowing. Remember, this was the rotation on up quarks, rotation on down quarks. So by analogy, how would the leptonic Lagrangian look like? It would be nu1, nu2, L, right? The analogy of up quarks. Neutrino is the upper component in the doublet. There will be gamma mu. There will be rotation that we could call the core, for example. And then there will be electron and muon, and W mu plus. And now I can use a language that this is the guys that mix, right? What is the convenient language? The convenient language is to speak electron with muon. These are well-defined particles. I know what the electron is. It weighs 0.5 MeV, right? That's a particle which is easily distinguishable from muon that weighs 200 times more, okay? So we often this for simplicity, right? G over 2, nu E bar, nu mu bar, L, gamma mu, E mu L. Instead of speaking of these two states, I rotate them, right, according to this picture, then nu 1 bar, nu 2 bar, this rotation that I call Poten-Corvo would be nu E bar, nu mu bar. And we can take a Hermitian conjugator from that. Okay. Why is this convenient, this notation? Well, first, there is no mixing, so that's convenient. But second, physically more important, it reminds me that what does it remind me? It reminds me that if I'm in a situation, if I have only one species, and that's, for example, the sun, there are no muons in the sun. I could even maybe dream of producing muons in the sun because the sun is very hot, but not that hot. You know, all kinds of crazy things could happen in the sun if the sun was hotter than 100 MeV, right? I could imagine. They would decay, of course, they wouldn't be steady. But we are safe. We know that sun is just like us here. Okay, there is proton and neutron, and there is an electron. So in other words, what I produce in the sun is not nu1. I produce nu E. And this is why we use this language of a coherent combination of two states. Then there is the rest of the story that Alexei talked about. And that is the question that there is a tiny mass difference. It's really tiny. You have a problem of even resolving that mass difference, okay? We have to understand this. Okay, I'm going to come back to this issue just to make sure that you got it, but I'm pretty sure that you know at least roughly what is going on. So, since in the beginning, okay, just to remind you, in other words, I created nu E in the beginning. This was the vision that Poten-Corvo had. Said if I get nu E in the beginning, then with time, it's going to involve e to the energy 1, t nu 1. It's some mixing angle, some linear combination, right? Some cosine theta plus sine theta plus e to the e2t nu 2 sine theta. E1 is necessarily different from E2 if they have different masses. So they will evolve differently. So it may happen if I wait long enough, or if I'm far enough from the source, that nu E becomes nu mu. It's not that nu1 becomes nu2. Nu1 is always nu1, right? It's a physical state that cares. Well-defined mass and spin and whatnot. Okay. This is this magical neutrino oscillations we talk about. But that also requires that they have different masses. Otherwise, they will have the same energies. They will evolve equally. So it's not surprising that when you compute the oscillation amplitude, and you knew it, or at least I recall vaguely that you knew it, right? That it was given by the mixing angle, and the mixing angle is maximum when it's 45 degrees, obviously. Okay, when it's 0, then there is no mixing, but it's 90 degrees, just for definition of what is 1 and 2. So it's not surprising that you get this. And then you get this beautiful oscillatory pattern, which require that the energies be different. There will be delta E which will appear, and that will give delta m squared. And then we often write the lengths here. They are basically relativistic. This is a tiny mass difference that you and I always forget about it, except when it appears explicitly, right? For everything else, they come out with a huge energy, right, out of the sun. The order of maybe hundreds of keV or MeV. And then we decided that the bigger the energy, the effect had to be smaller because the mass would matter less. And there was a factor of 4. Okay, don't cite me on this. And this is why we interpret this as particles having the mass, but we don't really measure the mass explicitly. Okay, this is our hope that one day we somehow directly probe neutrino mass. And this is also the reason we say that neutrino oscillations probe neutrino mass, because all other explanations fail, like decay of neutrinos and so on. Okay. And it may be useful to recall this in more detail. And to remind you how you come from this, but you said that you talked about K-on oscillations. So I could as well mention it now. But you know, it's not as clear. There the situation is a little murkier, you know, because it's much easier to talk. By the way, this is in the sun. Maybe before I go on, this is in the sun. I produce nu E. Therefore, it's not surprising that later on I may get another state if these guys are different, right? I mean, after all, what was this, right? This was just nu mu, nu E of t. Great. Okay, you know how to complete. And why do we speak of neutrino oscillations in the atmosphere? Again?
Because the distance, because of the distance.
Okay, but what is it? In order to speak of oscillation, remember, it is crucial that you don't produce nu1 or nu2, but you produce a combination Y. In the sun, because there is only electron. What happens in the atmosphere? How do you get neutrinos there? You knew, okay. Pions decay into plus nu mu bar. Pions also decay into electron plus nu e bar. So, why do we say that we get one combination? I mean, at first glance, I get both.
Muons decay like almost at the level of sea level.
Sorry?
Muons decay almost at sea level. I mean, not.
You decay into electrons at 3 level.
No, at sea level. I mean, at ground. I mean, they don't decay like in the atmosphere.
Yeah, they come down, right, but electrons don't even decay, so you're not going to lose electrons.
But you don't get neutrino electrons. You understand?
I said that in order to speak of neutrino oscillations, to even be able to talk of the phenomenon, to imagine it, it is crucial they produce only one combination of particle states. If I produce both, imagine that the sun has equally amount of nu E and nu mu. Then what would I get? I don't know if I would get nu E or anything. I couldn't even, imagine a scenario to speak of oscillations. Okay, I could speak of oscillations because I knew I produced only nu E.
Well, the branching ratio is mostly
in
muons.
Why?
Well, I remember our estimation 3 to the factor of beta.
Mass separation.
Because of the mass
The mass separation.
Why?
Yeah,
Because when you calculate the decay rate, it's proportional to m.
I know, but why? I know that you compute it, okay, I want to see physically if you...
I don't understand the question.
Because the mass difference between
you said that pions can decay to electrons and...
Of course, they prefer it. Normally we would say they will not decay into muons because the electron is much lighter. Your first impression would be that they are going to decay mostly into electrons and very little into pions, right?
Yeah.
Because the phase space is much bigger. No, on the contrary. Okay, just to remind you, the gamma of pion decaying into an electron and its neutrino, and pion decaying into a muon is proportional. When you say the small branching ratio, it goes as a mass square. A tremendous suppression. Okay, this you can compute. Now this is interesting. Okay, I can't help remarking here. I didn't plan to speak so much about that, but to this day you see these claims in the literature attributing this wrongly to the V minus A theory, to the chirality, to the left-handedness of the W interaction. You will find it even in the books or in the reviews. If you look at this beautiful review by Peskin at the Senju, it says that in the review. And that is not wrong, but it's not the real reason why it happens, okay? In the left-handed theory, take electron. Electron is so light that it's practically massless in the first approximation, you agree? So I want to see what will happen if I ignore electron mass, right? So how would the pion decay? I take pion at rest, and then I have electron going, say, in this direction, and antineutrino in this direction, right? But electron, our old argument, we can always use it, electron is left-handed, so its spin will go where? Massless. Let me assume that the electron is massless. Look, this guy has 150 MeV mass, right? So it's a good approximation. 300 times heavier. So the spin will be this direction.
In the opposite.
This guy, remember, it's an antiparticle, so chirality actually changes the helicity. So it ended up going right-handed, so the spin is. Can pion decay? No, because pion has spin 0. Take the angular momentum in this direction. If the guy is at rest, has only spin. Has spin 0. So in the limit, me going to 0, gamma, pion going into an electron is 0 in the limit me going to 0. This is a famous suppression. It goes quadratically, you can compute it. Actually, you should compute it once again, because I want you to have this for the rest of your lives. Because this argument that claims, the argument goes like this. I prove to you that when the interaction is chiral, that the guy cannot decay. It's true because interaction is chiral, because, but it's a wrong argument, because even if interaction were not chiral, pion could not decay into an electron. And I'll give you a hint. But first I want to make sure that you got this. This did not fail, okay? So in the chiral, remember my language, chiral means one chirality only. Okay, chiral interaction implies you cannot decay into a massless particle. Well, this thing comes from, from the weak interaction Hamiltonian, right? The pion decay comes, which would have EL bar, gamma mu, mu L, something like this, right? Electron going out, coming to W. I exchange the W. Then what do I get here in the quark picture? U bar or D bar? What do I get? Charge conservation. I should have, I want to have, anyway, I can think I want to have pion, what is P minus? That's U bar D, thank you. So I have U bar D entering, so presumably this was the interaction, right? I think this is good charge-wise. This I will get by exchanging W. Right. There will be an effective interaction for the G Fermi. But imagine that instead of left-handedness, you have electron, gamma mu, any combination. Let's imagine. Let's imagine that weak interactions were actually not chiral. Times this, right? Remember how I compute pion decay? I have to sandwich this between the pion and the vacuum. You remember that? Yes. There was this famous thing that if I sandwich a current U bar, even this if you write, you can write A plus B gamma 5 if you wish, D pi minus. This is famous F pion P mu. Gamma mu I should have, right? P mu. Remember, the piece that will contribute is the axial piece, right? Because pion is a pseudo-scalar. This is the definition of the pion decay constant. And this is the Lorentz structure, right? Sandwiching between the, you see U bar D sort of creating a pion. So when I sandwich that current, which gets the quantum number of the pion, it's going to give me a pion. That's a definition of F pi, if you wish, okay? The phonological definition, pion wouldn't decay if this matrix element was 0. Okay. You agree? It's just defining F pi. So remember, we would get here, what we will get here is F pi P mu by dressing this into pion. Did you compute it? Actually, was there a homework that you had to compute a pion decay? Did you ever sit down and compute a pion decay?
He did it.
You did it?
He did this in class.
He did it.
Okay, that's even better. Okay, so you should remember. So the argument that I used here, which was based on the chirality of weak interactions, okay, and was correct. Now, what I will get if I compute, I will get F pi P mu plus whatever coefficient, okay. I'm sketching it only because you said he did. I mean, notice we had a lot of experience with this. You've learned around what happens when P acts, Dirac equation, mass comes out. This is immediately the 0 when the M electron is 0. Of course, I'm taking neutrino to be massless, obviously. That's a Dirac equation. We used it, when did we use it? We used it a few times, but I forget now which. You should remind me. Remember how it goes. P is the difference between these two momenta. You go on mass shell and this gives you 0. Okay. All I have to remember that P electron, the momentum of the electron mu, gamma mu, E is 0 when particle is mass. So let's write ME. Okay, let's write the wave function of the electron. Spinner. The P mu, let's write better of the electron. Dirac equation, I use Dirac equation. So this is very interesting. This argument is extremely useful because you can see immediately that it's 0. But it's a very easy calculation that tells you that it didn't depend at all on the chiral structure. It's the Lorentz structure that comes out of the decay amplitude of pion that guarantees the famous suppression. Okay. It was not so important, but it's good that you know that. And that is, because Jorge was asking, this is why we know that in pion decay basically only muon comes out. This is 10,000 times smaller. It goes as a square, one has to check that, okay, you know that it goes to 0.
But muon can decay into electrons, right?
Yeah, sure. If muon decays, then you don't have decays. And the point is that muons can live longer, okay? Well, we'll go and I'll remind you, okay? The point is the muons that come out fast enough, they carry enough energy so that they don't decay, okay? We have to figure out, see, it has to do with the height of the atmosphere and so on. Okay, I'll remind you of that. All I wanted us to have the facts to that. From neutrino oscillations and neutral oscillations I get, I'm lucky that the physical processes in weak interactions, the states that are produced, both in atmosphere, is predominantly this, assuming it doesn't decay too fast, you're right, okay. I should take into account the muon decays, okay. That of course. But remember, even if it decays, only a factor of 2 will appear, okay. I can take that into account. that led to the fact that neutrino is massive. So let's attack the problem and then discuss the phenomenology of neutrino mass. Let's go to the heart of the issue. Why did neutrino mass become such an important topic? And why it became, you know, a window to new physics, okay? All kinds of new phenomena came from this tiny little number of less than an electron volt. So, neutrino mass. Standard model. What are the states in the standard model? Nu EL, ER. We decided not to put nu R because it simply is not there. Nobody ever saw it, and the minimal theory should address only the particles that exist. And you and I know that fermion mass, right? The fermion mass must have always this form, FL bar, FR, and plus Hermitian conjugate. We know that there is no right-handed neutrino, so you and I conclude, we don't have to be Weinberg, that neutrino mass is 0. This is a great prediction, okay, the clear prediction of the standard model, and it's based on the fact that the fermion mass must have this famous form. True?
Yes.
Is that true? No. What was the first homework you did? The first homework that you did. Actually, this proves what I'm saying, okay, and this is why this issue becomes so interesting. What I asked you to check in the first homework, okay, so let's have a reminder. This was a sketch today. We'll come to the issue of atmospheric. I won't discuss oscillations, solar oscillations. That's a fascinating subject, but it's highly non-trivial because we know today that they oscillate in the sun, okay. What did you do in that homework, if you remember? That if you have a left-handed fermion, which I could always write like this, you could introduce a quantity that we call the Murano spinner. A very strange quantity. Remember how I wrote it? Very strange theorem made out of the particle and antiparticle, a hybrid, you know, a hermaphrodite. This guy doesn't know whether it wants to be a particle or an antiparticle, okay? Or half the time it's a particle, half the time it's an antiparticle. The crucial thing is that I could write, or you could write, actually wrote it, what did you prove? That I psi m bar, gamma mu d mu psi m, the kinetic energy of this field was 2I UL dagger sigma mu bar d mu UL. Do you recall this? This interesting factor of 2. It's not surprising because this guy carries U twice. Once in the form of U star and it sort of works out that you get this factor of 2, okay. This, by the way, I could write in 4-component notation if I wanted. 2I psi L bar gamma mu d mu psi L. This, of course, is equal to this. Psi L. And why do I get sigma mu bar? Because I have gamma 0, gamma mu, which is diagonal, and it gives me sigma mu bar. Okay. What else you've proven? You've shown. So this is you guys, okay? This is the class. This is, okay, I'm just citing you guys. Okay, here. I'm not citing my run, for example. I'm citing you guys. then you show that psi m bar, psi m, is I UL transpose sigma 2 UL plus Hermitian conjugate. Do you remember that? Or if you stare at it for a moment. Now, why is it that I get that? Why would this bar give me UL? But look what the bar does. We are used to that. Okay, now I can go. This is all not true, except that instead of FR, for example, I could write anti-FR also. Okay, I'll come to that. It does take left to right. It's true, the master. But the funny thing is that the guy right, and that's the guy which is below, it's actually just the antiparticle of the other guy. So instead of getting something like U R dagger UL, I get UL. Okay, this is crucial. This is the strange Murano thing that he found, you know, his genius found by playing. Well, the way he did it, okay, I'll comment on later. It's not by using this chiral notation. By the way, I could write it. I think you will see that this is psi L transpose C psi L plus Hermitian conjugate. Let me see if you see this, that this is equal to this.
Yes, I sigma 2.
You should, because C is I gamma 2 gamma 0, which becomes diagonal, and it's I sigma 2. There is a 9, you agree. Both are of diagonal. So this was this mind-boggling thing, okay? I find this one of the greatest, well, the things written on the blackboard, it's sort of crux of the modern particle physics. Modern particle physics to me, and I think you and I will agree arguably, starts with Dirac equation and Dirac and Lagrange. This incredible thing that says for every particle, this is what came out of this beautiful little thing, for every particle, says Dirac, there must be an antiparticle different from that particle, same in the mass, but different. Therefore, he said at the end, he got courage and said, there is a positron. And positron was. Enters Murano, you know, another genius, says, well, not true. It's not true that for every particle there is an antiparticle. I have a guy that is its own antiparticle. He imagined that this was the neutron. At the time when Murano wrote the paper in 1937, people didn't know that neutron was actually not neutral. Well, what do I mean by that? Neutron carries zero charge. Well, it has a magnetic moment. It's not completely neutral. Why? Because sort of, in some sense, neutron knows that it's made out of these charged particles. And then it wasn't his, okay, people realized, well, this can apply to any neutral particle. You don't want to apply this to a charged particle because this would automatically break charge. And you found out that the current vanishes, okay, charged particle, you couldn't have that current, okay, this was nice. Why? This obviously breaks charge, right? I can't put a particle and antiparticle together. There will not be charge symmetry. And this obviously will break charge. This is an electron. Another way of seeing it, the conservation of charge is set so well that I think the electron, we should call this, so we should have a name for this thing, and let's call it Murano. So Murano mass term of an electron divided by the Dirac mass term of the electron is less than 10 to the minus 20, I'm sure, or less. Okay, I can try to dig up the number. We can do it together. It's an extremely small number. I guarantee you that it's less than 10 to the minus 20. Okay. Charge is well tested, charge conservation. It has to be small, otherwise charge will be broken. But neutrino could carry that mass. There is nothing that prohibits it. As far as we know, neutrino is neutral. As far as we know, it has no magnetic moment. Nobody ever measured magnetic moment. Okay, it's truly neutral, as far as we know.
I have a question.
Please.
Why?
Oh, this I want us to, please ask any questions, okay? This is the sort of
How can we have
basics
a
of-
Murano mass of an electron? Because it's a charge particle.
Sorry?
How can we have a mass term of a Murano mass of an electron?
Well,
Because it's a charge particle.
Well, how would we have it? If it had a Murano mass term, charge would be broken, it wouldn't be a good symmetry. How do I know the charge is a good symmetry? By doing experiments,
Yes.
and I found the charge wants to be conserved, and it's a good symmetry. And one of the experiments I have to do, I have to find a way of measuring the Murano mass of the electron.
I mean, it's a measured quantity, right? This mass.
The limit, well, it's not measured, it just says that it has to be very small. If charge will be broken, for example, what could happen? See, I have to find the indirect consequences of the charge breaking. I'm going to have to think of the indirect consequences of neutrino maybe having this mass. Well, you knew it. It's called neutrino double beta decay, you knew it. We can think of some more. You and I could try to figure out, okay, it's the task of today. Anything that you can come up with that will prove this new thing if it exists, okay, if it paves the way to new physics, okay. If charge is not conserved, why do we believe that charge is conserved? Because we don't see this decay, for example.
Yes.
And it's very strange that we don't see it. The electron likes to decay into a neutrino. It's so much heavier than a neutrino. But what does it mean that we don't see it? Well, you put a limit. You have some idea how big it is?
More than the Asian here.
Just to see if you have any. You want to put a number? Guess. You want to make an
10
educated guess.
30.
Into the 31.
Actually, it's not 10 to the 30. It's around 10 to the 26, I think. Please,
Okay.
let's check it in the particle data group. Last time when I looked at it, it was around 10 to the 26 here. And this is very interesting. Maybe Guillermo will find it while I would appreciate it. If you, huh?
I don't know where to look.
Maybe in the, or it will not be in the properties of the electron, who knows? There should be conservation laws. There must be a review on conservation laws, so charge conservation will be discussed. While you are trying to see, I just want to comment, this is interesting, that remember the limit on proton lifetime is much better. It's almost 10 to the 35 years. Yet, if you talk to any colleague, any peer of mine, anybody in our field, most people believe that proton decays. And almost everybody believes that electron is stable. And it's not just a prejudice, okay? Of course, we never believe there is a good degree of prejudice. You try to construct a theory with broken charge, you will see that there is no way of having consistent QED if the charge were broken. It is crucial, the conservation of charge, which is a topic that fascinating topic worth maybe discussing in a different occasion, okay? But forget it. Our prejudice, the fact that I cannot imagine a theory that gives me this, okay, helps me believe that electron. So I, for example, never work on the possibility of electron decaying, but I spend a lot of time working on years of my life worrying about proton decay, which we don't see.
Yeah.
So if I can write the Murano mass for the neutrino, why is it that we don't write it? Why doesn't Weinberg write, or Salam, or whoever?
How did you?
Or why didn't Smirnov say, or why don't I write?
How did you get the hits? How do you couple the hits together?
Very good, but why don't I just write it, okay, very good. How would I couple two hits? An excellent question, okay. But I can ask you, so this is invariant apparently in the notation I've just introduced here, which is your homework. This is Lorentz Invariant. By the way, you know what it is. Why is this invariant, just to remind you? Remember we found it in SU2, these are two spinors. Like in antisymmetry is two spinors, okay. And boosting is very similar to rotations, okay? The only difference is the extra factor y in the transformation property, right? When we use the compact Pauli. And that, of course, because of transpose makes no difference. Under rotations, just to remind you, I think it's good here. Under rotations, UL bar, UL is invariant, you agree? Trivial. UL transpose, I sigma 2 UL is invariant. Under boost, well, UL transpose I sigma 2 UL is invariant. Because, I mean, how does UL transform? Well, it's always I sigma over 2. This is how it transforms times some psi. Psi vector is theta, Euler angles 3, plus I, phi, rotation, boost. So whether there is a factor y or not, it's irrelevant when I write the transpose. So this is invariant. But what about this? Is this invariant? UL dagger UL? No, here the factor y kills you. This is not invariant. What is invariant is UL dagger UR. You have to introduce UR if you want to write in this manner. Because when UL transforms like this, how does UR transform? Psi star. So this is invariant. This invariant is called the Dirac mass invariant. I need two different spinors to get the Dirac invariant, which I have at my disposal, because if I want to talk of the electron, okay, this is what we learned from Dirac, there will always be a positron. Or if there is left-handed electron, there must be a right-handed electron. But right-handed electron is just like a left-handed positron. Okay. Remember this thing, the charge conjugation, what it does. Takes a left-handed particle into a right-handed antiparticle. So I have this. And this is why I needed a 4-component spinor to speak of the electron. This is why there is electron in the positron. This is why there is the theorem for charged particles. Dirac is right, of course, but he wrote the equation for charged particles. Dirac was not completely stupid. And concluded that every particle there must be an antiparticle, right? He said it in 1931, in 1932, Anderson found a positron, and in the 50s they found an antiproton, and so on and so forth. But neutrino, being neutral, is allowed to have this. This is invariant under rotations and under boosts. Well, you did it. You explicitly constructed it. So why is it that I don't write this master, which would be UL transpose, I sigma 2 UL, where nu L would be written as UL2. That's what I mean by, this is not an up quark, okay, this is just the 2-component neutrino written in the spinor notation. Why is it that I don't write it? Why is it that Jorge wants me to think of Higgs? Why didn't I write the electron mass? It was the symmetry that forbade it. I couldn't write the electron mass either. When I tried to do it, EL bar ER, I couldn't because I didn't have a singlet out of a doublet in the singlet. This was forbidden. I didn't know what to do, so I decided to stick a scalar field. It had to be scalar, right? The rest is history. Same thing here. This is a doublet, this is a doublet. Well, you can say, oh, maybe it's a singlet. Well, it's not a singlet because look at T3. What is T3 of a neutrino? What is a C3 of a neutrino? This is not 0. The Lagrangian must be scalar, cannot carry spin, weak spin, whatever. So it's true, this is a Lorentz invariant. This could have been invariant. The same way that this was Lorentz invariant without the Higgs. This was Lorentz okay, but not SU2 okay. So I stick a Higgs. I don't have a, what can I stick here? I can't couple it. I could do that because this was a singlet and this was a doublet.
Yes.
So even if I take the Higgs, okay, someone gives me the Higgs, Higgs give me the Higgs, okay, Weiner gives me the Higgs. So I try to do it, I won't here, right? It won't work. At dimension 4. Because I have to actually it could work if I allow myself to go to higher dimensions, but I wonder I wonder whether you would see that. By the way, once you and I decide to respect the standard model gauge symmetry, which is SU2 plus U1, then we don't really like this. We write this in a manifestly SU2 invariant notation. Right? I take this doublet, which I call the leptonic doublet. We want to stick to a manifest notation. So obviously I couldn't even think of writing like this. I should start with a doublet notation. I have to imagine something like this. L transpose L. And you see, I know immediately this is not going to be an SU2 invariant if I take this twice. Can you try to get, okay, but I can, this is the way I should write, and then see what I have to stick. But think here, just for fun, if I break this into, I can erase this. This was the first homework. We did the Lorentz group in the two-component notation. Okay, this was very useful. I'll summarize it. I should summarize it and keep it on the blackboard. Once I go through this. Please remember, this is EL dagger, phi 0 ER, plus nu L bar, phi plus ER. If I write explicitly a doublet. And then I don't worry about this because I work in the unitary gauge where phi plus is eaten by W. So I don't even think about it. Remember when I go to normalizable gauge, okay, then we have to rethink. And we'll have to rethink. But you see, you can understand the Higgs mechanism at the level of the components, which may help you see what is going on. And you can say, this must be SU2 invariant. So let me look at T3 of SU2. What is this T3 of EL? Minus a half. So it's plus a half. T3 EL bar. It's an antiparticle. What about phi 0? T3. It's a doublet. It's minus half. It's neutral. I think this is what confused. I think. Good. Okay. Minus a half. What is T3 over ER? So see, it is a singlet. Okay, I can see that. Okay, and I could, even if you don't know group theory, you can just think, if you know the quantum numbers, you say, look, you say without phi 0, T3 is broken. I have to stick a particle with a T3 minus a half so it can work. Now look what I have to do here. Let's try to do the same thing here. T3, 1/2. So if I want to make this invariant, what would I need to get T3 0, what would I have to do?
singlet.
Maybe. Well, no, I could introduce a new Higgs, but then it will have to be T3 minus 1. And that will be a what kind of Higgs? Triplet. Very good. So if I were willing to introduce a new Higgs, I could give them a mass. Actually, people do that. It is one of the well-known models on neutrino masses. If I don't want to do that, I say, but I just can't stand any new states. What would I have to do? Two, right. Two. I could put 2 of these 5 zeros. The only thing, the dimension will go wrong. The quantum numbers will go okay. It will be a minus half. This would be perfectly invariant, but we would have dimension 5. I'm not allowed to write the dimension 5. In other words, what I know that this has to be divided by some scale.
Yes.
Let's call it W, not for weak, but for Weinberg. Actually, Weinberg wrote this. You and I are not allowed. But Weinberg is, kidding aside, Weinberg says it may still be useful to write such an operator, not that it's there in the standard model. Just the way Fermi wrote weak interactions as an effective theory. So then one day you figure out where this is coming from. Weinberg said, well, I have to understand where this is coming from, but in principle, I could have a neutrino mass if somehow at the end of the day. But you and I have to understand, well, okay, he says, but where is it coming from? We don't want that. I'm going to pause now and ask you how we could ask, maybe in a more elementary manner, in a natural manner, extend the standard model to get neutrino mass. And we should remember, in other words, that, let me summarize on the right hand side, I want to raise it, this important thing. That there are 2 invariants. One is psi L bar, psi R. I will call Dirac. And there is psi L transpose, C psi L. I will call Murano. We have to remember that they are always possible. We have a rule, we have a tacit agreement, you and I, we will write this only for neutral particles, okay? Because we are not going to break charge. This is a conventional mass term, so in other words, these are mass terms for spinors, which are fermions. Notice, why did I actually make a go through the, we could have worked at the 2-component notation, but what was useful with what you guys did, you showed that you could use the same Dirac notation, you ended up with the same picture that Dirac had. Only your spinor was a little funny, okay? Psi Murano. On the other hand, psi Dirac would look like UL, UR. It requires 2 different spinors, okay? Completely different. They have nothing to do with each other. They are irreducible representation of Lorentz group, independent from each other. But the bottom line is that the Murano Lagrangian has the same form as Dirac. So you can use the same propagator if you wish. You can use the same Feynman rules. Okay, this is very convenient. This is the advantage since you and I are used with the 4-component Feynman rules. Okay, it's good to have this notation. But the nitty-gritty is here. It boils down to this invariant, which boils down to the possibility of anti-symmetrizing spin. It's all there. Okay. So since I don't want to do this effective operator approach of Weinberg, I want to have a model on neutrino mass, a physical model what would be the most natural thing? Our conclusion was good. Neutrino is massless for two reasons. There was no right-handed neutrino, and I couldn't write the Murano mass term because the symmetry of the standard model. Okay. But the most natural thing, the simplest thing that we ended up that became a canonical answer to the question of neutrino mass. 90% of the workers in the field simply said, well, why wouldn't you introduce a right-handed neutrino? It's the most natural, the simplest extension that you can have in your mind, and it becomes symmetric. Now the quarks and lepton become symmetric, so if you like this, in every other sense they were symmetric. Notice how they come in generations, okay? This interesting thing. You don't get quarks without leptons, so that's good. And I can prove to you that the standard model would not be consistent if quarks didn't come together with leptons. It has to do with something which is called anomalism. So if you don't mind, let's introduce a right-handed neutrino. It's almost becoming a standard model today. There is Misha Shaposhnikov in Switzerland and collaborators who often use the language, they will call it a new standard model. Not new, but new standard model, because it's maybe a fair language, okay, because I have to have neutrino mass now that I know that it's massive, okay. So let's write down the, okay, without any further ado, let me write down then the Lagrangian. I would have a kinetic energy. In other words, let's call it neutrino Lagrangian. It would look like this: I nu L bar gamma mu d mu nu L plus I nu L bar gamma mu d mu nu R. So all I need is this, and I need a Higgs doublet. And then I write minus. I would write the Yukawa interaction, which I would write by analogy with electron Yukawa neutrino, L bar. Remember how I log the electron? Nu R. I had dr and phi here. The quantum numbers tell me, can I put phi here? Let's try. Yeah, it's a doublet, it seems. What about hypercharge? Let's check. Do you remember hypercharges? Do you remember the hypercharge of the Higgs? It's 1. Nu R, you should know it immediately. I shouldn't have to ask you. Even if you're still sleepy like me and you sleep much last night. No, it's twice the charge. It's T30. So it's -2. And L? Well, L had -1. You know, it won't be +1. It has to reproduce the electron with the charge -1. These are -1. This has hypercharge, so L bar has +1. I'm saying something. What, nu R is 0?
Yes. Yeah.
I was thinking of it. I didn't sleep much last night. I'm sorry. Good. You were awake. You didn't insist, you know. You cannot trust authority that much. Okay. So it fails here. Of course, it worked for the electron. This is how we got the electron mass. So what should I do? The usual trick. I did for up quarks. I use phi tilde. Phi tilde, which is, remember that there is always phi tilde also, which is I sigma 2 phi star. It's just like phi star. You multiply the I sigma 2 to get the correct SU2 quantum number, okay. Then it's okay. Remember that for us phi is phi plus phi 0, because phi plus gets eaten, and phi tilde is phi 0 star minus phi minus. So what do I learn? I learned that neutrino gets a mass, just like the electron. Why? Because this will be nu bar E bar L, and phi tilde would be, I would have H plus V, I would have the web, and whatever I have here, 1 over square root of 2, and then I will have nu R, and nu L, nu R gets me a neutrino mass, and I would learn that M neutrino is Yukawa over square root of 2 times V. Correct? So what would be the physical consequence of the neutrino having a mass? Well, there will be oscillations, of course. Oh, what else? You know, the beautiful thing we learned about the Higgs mechanism is that it leaves a physical trace that associated with Yukawa coupling, I get Higgs decay into that particle. As you know from the homework, gamma Higgs is proportional to Yukawa squared. From here. Therefore, Higgs decays also into a neutrino. Neutrino is mass. Of course, it's going to decay into a neutrino. Gives you mass, decays into you. But you see how small Yukawa is. I can now write that Yukawa over square root of 2 is m nu over v, which we remember, if you remember the mass for W, it looks like g over 2 m nu over mw. So what do I conclude? That neutrino mass is a lousy window to new physics, to anything. I just stick a right-handed neutrino, and I found out that, okay, yes, there will be some new physics, Higgs is going to decay, but look how small this number is. Let's estimate it. This is 100 GeV. This is less than an electron volt, which is 10 to the 9. So this is less than 10 to the minus 11. So there will be a branching ratio of Higgs into a neutrino, which is invisible, of the order of 10 to the minus 22 or something, or whatever. Less than that, because actually there is some suppression. Sorry, maybe slightly bigger. No, I didn't want to say anything. But and remember what that Hoff taught us, okay? What I taught you, I claimed that Hoff taught us about renormalizability, about the rule for writing down the gauge field theories. You should write all the interactions allowed by symmetries. Take a gauge symmetry in question, SU3 color. I don't have to talk about it, this guy carried on color, times SU2 cross U1, and write down the most general Lagrangian. That should be a prescription. The question, did I write the most general Lagrangian? Let's go here. I wrote the kinetic energy for left, kinetic energy for right, and I wrote the Yukawa coupling just like I did for the electron. So it seems yes, but actually no. What did I forget? And you too. That I taught you today, and you did in your homework. Erase this because this is actually in general not true. Let's come back. I forgot something here. This is not the whole story. We ask ourselves a question. Can we write a Murano mass for left-handed neutrino? And we said no, because it would violate SU2 cross U1. Can I write a Murano mass term for right-handed neutrino? Well, it's a singlet. The answer is yes. This guy is a singlet. This guy carries no quantum numbers. You knew that. Carries no charge. Carries no SU2 cross U1. Therefore, the Lagrangian should look like this. minus, I don't know, let's write like this, M nu r transpose C nu r plus Commission conjugate. Oh well, let's write like this. So I don't need a bracket here. This is the most general institute corresponding angle. It changes things completely, obviously. Well, first things, you know, what I needed before, if that was to be the whole story, neutrino would be light because I would have to stack in some crazy Yukawa coupling 10 to the minus 12, which is a bit strange, because neutrino and electron live in the same tablet. So it's kind of strange, you know, this is brother and sister, and one is orders and magnitude lighter than the other. I mean, charm and strange quark, there is some mass difference, it's true, and top and bottom, but not a million times smaller. So, when this was realized, it actually changed, you will see, changed the way we look at neutrino mass and paves the way to a lot of physics. So I don't want to call this Yukawa neutrino. I'm just going to call it Yukawa Dirac, because this is a Dirac mass term. I should remember that both are allowed. Dirac, when the quantum numbers allow it, Murano, when quantum numbers allow it. The only thing now, how to work with this. Okay, this is going to produce, we said Yukawa Dirac, nu L bar, nu R, times V, over square root of 2. By the way, I'm going to call this M Dirac, nu L bar, nu R. There are now two ways we can attack this, okay? Because we are sort of confused here. I have my random mass term, my Dirac mass term. How do I make sense out of that in a Lorentz sort of consistent manner, right? Well, one way that the homework taught you, why don't I construct the Murano states out of these guys? Now that I know that Murano mass is allowed, in other words, I can introduce the following two states: nu, which is nu L. Oh, I could have said here, it would have been useful. Dirac, you know, another thing in this box here that we don't want to erase today. What is psi m? It's, notice that this is psi L plus C psi L bar transpose. Why? Because this is psi L plus I gamma 2 gamma 0, another gamma 0 from here, psi L star, which is psi L plus I gamma 2 psi L star. This is precisely, it checks, right? This is the same thing. This is gamma 2 is off diagonal. And psi L is UL 0. Everybody sees it. Okay. I paused for a second. I don't want to lose you here. Okay, in other words, I can introduce this state. And I can introduce this state now. Let me call it N, because it's some different state. Right? Notice what is happening. I'm splitting the world. Whereas in the case of charged fermions, we talk of one and the same particle, electron, left and right together. Here, since this has nothing to do with them Dirac, and they may be widely different, I should speak of two different states, left and right states, because of this Murano freedom, or I may call it nu and N. So this would be nu R plus C nu R bar transpose. It's just a name introduced here. These are Murano states, okay? I don't want to put a Murano index here. This is this. I'm doing it separately for neutrino left-handed and separately for neutrino right-handed. And now I can proceed and I can use what you guys taught me from the homework. Because what you have shown, Jorge.
I'm writing the Majorana term or neutrino, but we cannot, I mean, we're not allowed to write Majorana term neutrino because of the quantum numbers.
Oh, I didn't write. Yeah, I decided not to write it, not for neutrino. Right? Because SU2, I'm writing a Lagrangian which is completely SU2 cross U1 symmetric. I produced M Dirac because I allowed myself to break the symmetry spontaneously. That's okay. Symmetries can be broken spontaneously because we found out then, because of the residual gauge freedom, the memory of the original gauge freedom, we can write the correct propagator. Remember, that was the whole, it was the essence of doing it spontaneously. But we won't write, there is no neutrino master here with itself. Neutrino only couples to nu R.
And nu?
Yeah.
Nu also we are keeping nu L as Majorana.
Well, I just want to see what happens. I'm guessing. You see why? I'm guessing here. Look, this guy is getting its own Majorana mass, and he can only have Majorana mass. It's coupled to nu. Somehow it's going to carry the information to nu. It's going to tell him that he can have a mass, right? Because now I'm going to get a non-trivial mass matrix. Well, I should finish diagonalizing the mass matrix to see what happens. But yes, I would guess, without doing any work, that the left-handed neutrino will also pick up a Majorana mass. I couldn't write it because the symmetry forbade it. It will do it from M Dirac. I had to introduce Yukawa Dirac and I had to break symmetry spontaneously, and then I argued that I should be able to produce a Majorana mass term for neutrino. This is what, by the way, Weinberg tells me with that higher dimensional operator. He says, if you have some new physics and you integrate out, then at the end of the day, neutrino will have a mass. You see, like Fermi taught us, if you have new physics and you integrate out, you may get neutron decaying into a proton. And we introduce a new physics, right, in the standard model, Gleshow, the idea as existed before, took us to the road with W boson and we integrate out. So yes, here is anticipation, good point. It's a sort of educated guess. But the end will justify what I am. Because now what I have to do the exercise that you guys did, I have to write this. All I have to compute is master. So, for example, I find out that n bar n, where should I write it? Maybe here, okay. N bar n is nu R transpose C nu R plus Commission conjugate. This is what you showed to me in the homework. Now I'm citing you. Okay, I hope you remember that that's what you did. This is here. After all, it's here. And I can show in the same manner that nu bar n is nu L bar nu R plus Hermitian conjugate. In exactly the same manner, I can show that n bar nu is nu L bar nu R is nu R bar nu L plus Hermitian conjugate. These are equal. How will this go through? Just to remind you, let's write this here. This leads M Dirac nu L bar nu R. There is a Hermitian conjugate. Now, how do I get this, for example? Well, let me show you how this will work. Nu bar would be nu L plus C nu L bar transpose bar nu R plus C nu R bar transpose. So the first with the first will give me nu L bar nu R, and then the second with the second, you can see what happens. You see bar and bar, we get rid of the bar. And I have new R bar here. All I have to rotate it and use the property of charge conjugation method. This is what you did in the homework. In exactly analogous manner, you showed that this is new R bar and new L, which is what I wrote before. And this is new R bar and new L. They are actually equal. This new L bar and new R. So when the dust settles, this Lagrangian here becomes neutrino. There is a factor of half. These kinetic energies from what you guys have shown had a factor of 2 here. So I will get nu bar gamma mu I d mu nu plus I n bar gamma mu d mu n. There will be a kinetic energy minus 1/2 md nu bar n plus md n bar nu. I'm writing this, you will accept that md is 1/2 md plus 1/2 md. So I split a half into nu bar n and a half in nu bar n bar nu because they're equal. And then we showed this thing. So I forgot here that to write this as m over 2. There was a factor of a half. There was a factor of half. You see, in order to call it a mass, you remember there was a factor of half. So I have plus n bar n. And I'm going to write this mass term mn. I'm going to call, and here m nu r over 2 is mn. Or is equal to mn, I'm sorry. No, m nu r is mn. Why should it be a 2? There was a half, and I keep it. Because of this relative factor of 2, when you do the kinetic energy, the mass term here is not the mass term, the quadratic piece. You have to normalize to kinetic energy. The overall factor of 2 does not matter, right? I can get rid of it. I get the same equations, okay? So you have to bear with me, for we won't take long. We are almost there. I think I get to erase this now. I need it. If you have forgotten this, maybe the first homework can be the fourth homework. I mean, looking back. I wanted you sort of to get into 2 components, spin and write those masses, but there is an advantage. I remember when you came after the homework, okay, you were full of that energy of having just checked it, and maybe by now you forget it. Anyway, notice that now I have a mass matrix between u and n. This will be nu, this will be n. I have 0 here. Nu cannot couple to itself. That's an SE2 symmetry. But it can couple to n. And this way produces a 2 times 2 matrix. And the trace of this matrix is Mn, and determinant is minus m Dirac squared. So the eigenvalues, I have a quadratic equation, x squared minus mnx plus md squared minus md squared equals 0. These are the eigenvalues of this mass matrix. I have the usual quadratic equation, right? x12. It looks a bit messy, but if you just vary plus or minus square root mn squared plus 4 md squared over 2. It's not yet very illustrative what I'm doing here, but it will become in a second. The interesting thing is that M Dirac is an SU2 ×1 breaking mass term that naturally wants to be small. I mean, think of the first generation. Let's just think of neutrino and the electron, right? In the case of electron, it's a very small number. Whereas this is an SU2 ×1 invariant number, which has to do with some new physics, okay? So the next assumptions that one makes, that Mn is much bigger than M Dirac. I will justify in a deeper manner, not here, okay, because at this point it's just an assumption. But it's fairly natural. That we know that this will come. After all, what is this right-handed neutrino? It's some new state that has some new physics, okay, that eventually I will understand what it is. I just stuck it in the standard model. If I assume that, then I will have a heavy state. Take a plus sign there. What do I get? Mn and expand plus 1/2 2mn plus 2 m Dirac square over mn over 2. Take mn out, and I will get 4 m Dirac square over mn squared, that coefficient, and it's just a half, right? I'm expanding a square root. So this is mn, so roughly, mn plus a tiny piece, m Dirac square over mn. And this is heavy state, and the light state, I would have a minus sign here. The leading piece cancels, obviously, right? If mn is very large, what did I get? Minus m Dirac square over mn. They're both Majorana masses because they involve only two component states. They cannot be Dirac masses, they're Majorana masses. I mean, what happens is that it looked like a Dirac situation, but because they mixed, this guy actually transferred some of its mass to this guy. Notice in the limit that when n goes to infinity. So what do you learn? Okay, the lessons we learn. Mn going to infinity. What do I learn? It has to. I'm back in the standard model. By the way, look at this matrix. Forget all the gymnastics that I did. In the limit when mn is large, the determinant is minus m Dirac squared. One state is mn roughly. So the other state is obviously m Dirac squared over mn. Determinant is m Dirac squared. This is a check. This we are going to ignore if mn is really large. You see, m Dirac squared over mn becomes double suppressed. It's not just because Dirac is small, but it's Dirac squared. I mean, just to give you a feel. Just to give you a feel why this could be exciting. So this is direct. We can see directly what is going on in what is called a seesaw picture. This is called the seesaw picture. This particular picture, by the way, it didn't emerge in the standard model. There are a bunch of us that came to this from different ways. Gell-Mann, Ramon, and Slasky, for example, one of the fathers came from grand unified theory. Minkowski and Mohapatra and myself came to this from working on left-right symmetry, whatever it is. Okay, the thing is, okay, you know, Gell-Mann was a great physicist. He's a great physicist, he's still alive. But he was at least as good with names as he was with physics, okay? He was somehow, you know, I don't know, or maybe he didn't think of it. Maybe it was Ramon, actually, I think. Or Slansky, who's... But, you know, I would have never thought of that, okay? The idea, he says, you know, it looks like a seesaw. You have this guy, the heavy guy, you know, and then you have this little guy, nu, which is very light, okay? And it's there, you know, it's very light. These heavy guys gave it a little mass. So somehow what the heavy guys did, and you were just, by talking to this heavy guy, we use this language when n becomes very large, we say that we integrate it out. The heavier the n is, when you completely integrate it out and let it go to infinity, then of course the mass disappears. But if you keep it there at some large scale, okay, and forget about its role at low energies, you are left with a light Majorana neutrino in a natural manner. Or
so just to remember, in the premise for this model is that neutrinos have to be Majorana and they have to be...
Well, we just wrote the most general. You don't have to say that they have to be. We just wrote the most general Lagrangian.
But there is also a neutrino, a singlet right-handed neutrino. And at the end...
Yes, well, we should find a good name for this right-handed neutrino, because it's not a neutrino. The guy apparently is very heavy. So it's a new heavy neutral lepton, we should call it. I don't know what to call it. The right-handed name stick because of this funny thing. Remember that actually when you speak of Majorana, it doesn't make sense to call them left or right-handed. Remember, half of that was particle, half antiparticle. Half was left, psi Majorana, psi L, plus C psi L bar transpose. But this is psi L. You could write like this, plus psi C, right-handed. Remember, this becomes right-handed. It goes down. We wrote it, okay? So it's sort of both left and right, the name stuck, but it's not a neutrino. Okay, its role here, it lives here only, in the standard model picture, it's sort of the only reason it lives here is to, you integrate it out and you get remember what Weinberg says, I can produce a left-handed neutrino mass, a Majorana mass for left-handed neutrino, because this is what we did. If you allow me to stick twice, phi 0, and divide by some scale. I could put some coefficient here, but I can hide it in the scale. Notice that we did that. Actually, at the end of the day, we did what he said, because our neutrino mass is m Dirac squared, but m Dirac, remember, is Yukawa Dirac times phi 0. So at the end, it has to be the way he said. At the end of the day, you'll get the same thing. So there is not much use here of doing what he does. Is just a language of this kind of phenomenon. You can also complain, and you can say, and now it's the crux of the issue. And you can try to see whether I cheated or I didn't cheat. Did I really? Okay, this is claim. The sort of claim is the conventional wisdom. The wisdom of the day says, neutrino is light. What does it mean that neutrino is light? That it's much lighter than the electron. I have to compare to the measure full number. It's equivalent that Mn is much bigger than m Dirac. Whereas this was very strange to people because they live in the same multiplet day. People found this very natural. This m Dirac is a doublet kind of mass term from symmetry breaking. This is a singlet, okay? Or if you wish, mu, m Dirac square, forget the mass or forget the sign for the moment, m electron equal to m electron Dirac. It has only a Dirac mass term. Electron does not have a Majorana mass term. So you ask yourself, if what I'm saying is natural, suppose that they are similar, which is kind of encouraged by the fact that these two brother and sister, these two relatives live in the same multiplet. Then I would actually predict Mn, you agree? Because M nu, okay, maybe it's better to say M nu would be of order Me squared over Mn. If this naturalness were to hold true, then what would I get for Mn? Would be Me squared over M nu. So what do I get? ME is, let's do it in GeV. Help me here not to make a mistake. So this is about 10 to the minus 3. So this is 10 to the minus 6 in GeV. So I'm going to have GeV. A neutrino mass, let's take tenths of an electron. Which is 10 to the minus 10 in GeV. Correct? Well, actually be 1 electron volt even. I don't know, neutrino could be all the way to 1 electron volt. Let's take this limit, okay? Let's not pretend that we know more than that, okay? For neutrino oscillation, we only know the mass difference. So, what do I get? About 10 to the 3 GeV. Okay, because I sort of, the conventional visit tells you, oh, you know, I can tell you why neutrino is light. I can explain it. I'm excited. I don't sleep the whole night. Actually, we got very excited when he did that. I try to tell you for different reasons than what is normally said. Because I could come and tell you, I know why neutrino is light. You say, yeah, I don't relax. No, I know why. Apparently, when, you know, in the old days, there was a smaller number. Every summer, people then to get together in Aspen, theoretical physicists. It's sort of a extended workshop that's been going on for the last 50, 60 years. So in the early 60s, there was a small group of people. Gell-Mann started this. So apparently, once there was a sketch, he comes to the stage. You know, they would relax in between talks. He came in, you know, he says, you know, I'm a Murray Gell-Mann, I'm a genius. He says, I know what particles are made of. Everything in the universe is made out of quarks. And then there are two guys dressed in white, they come, yeah, everything is going to be okay. No, I'm a genius, I know that, you know, and then slowly, yeah, relax, okay. I could tell you I know that neutrino is light because then it's heavy. But is neutrino light because M is heavy, or N is heavy because neutrino is light? I don't know, because I don't know what Mn is. I don't know what this guy is. I just stuck in a particle whose properties I have no idea about because it's a singlet. See, the beauty of the standard model when the particles are not singlets. You can study the properties because they couple to the W and Z and so on. But here, this guy is a singlet. Well, you can say, okay, but look, in this natural picture, it could weigh 10 to the 3 GeV, and you could produce it at the machine in the border of Switzerland and France. You know, there is a big machine that you can produce particles that weigh TV, and that will be very exciting. How would you produce it? You see, once, you know, you have, and I think this is very important, okay, I'm about to stop. If you want to explain a physical phenomenon, you should have a new prediction that could be verifiable. Otherwise, who cares that I have a language? You know, at this point, it's only language. So you and I have to think, could I really produce this guy? After all, the guy is a singlet. How would I produce it? If I can't produce it, I think you should agree with me. Then I explain nothing. Okay. So maybe we can address this issue. If I could do it, and maybe even address a more important question, what could be the theory beyond the standard model that could tell us that this particle exists and how to look for it? Because somehow in the standard model, it's really a phantom state, that it's more of a trick of writing a Murano neutrino mass than, or if you wish, You know, the same thing I would have told you about the W boson if you don't have a theory of W boson. Or if you cannot produce in the experiment or both, then use Fermi language. It's a better language because you are describing the same phenomena in a coherent manner that you can go and test. So unless I can produce a right-handed neutrino, I erase it on purpose, Weinberg's operator. Then Weinberg's operator is a better language. He just says, forget it. You see, at the end of the day, he says what happened is that you have a small left-handed neutrino mass, which I knew anyway, Weinberg says. It's of the form phi 0 squared over some scale. And what is the scale, by the way, Weinberg scale? One of the, I should have written this and now I finish here. It's Yukawa Dirac square over the mass of the right-handed neutrino. Because what we have is m Dirac square, which is Yukawa Dirac, divided by m. So the way we are going to proceed, we are going to try to see if there was a simple physics, and most important, if there was a way of looking for this guy to really speak of the original neutrino mass, and even more important, even if you don't succeed at how would you and I test that neutrino has a Murano mass, because this picture at least has one clear statement that if neutrino is massive, it should be Murano. And I want us to understand a little better the formalism of Murano, okay? So we'll be coming back and forth to the things we touched upon today. Any question, please? Okay, let's stop for today.